Hello everyone. Today's lecture we are going to look at example problems that involve 2D stress transformations. For the past two lectures we have looked at how to transform stresses from one coordinate system to another. For the case of 2D stress we looked at the concepts of principal stress, principal planes and the maximum shear stress. Today we are actually going to kind of use some of those equations that we derived to actually solve problems and also use the method of force equilibrium to find out stresses in arbitrary planes. So if you think about the stress transformation concept that we learned, essentially what we are doing is that if you have a point and you know the stresses at that point on specific planes, so two orthogonal planes that pass through that point, then essentially you can use the stress transformation equation to find out the stress at the exact same point on different planes that pass through the same point. Okay, so again, the point is the same. It is just that the planes that you're looking at are going to be different. Okay, so that is the idea of stress transformation. Okay, so that is something that I want you to keep in mind. Okay, so what I'm going to do today is look at some examples, okay, where we find stresses in arbitrary planes that pass through the same point, in which we already know the stresses in some particular planes. Okay. And then we are also going to use the force equilibrium method. Okay, so effectively at the end of the lectures, you will essentially be able to use this 2D stress transformation equations that we derived in the earlier lectures to compute stresses in different planes. And secondly, use force equilibrium to compute stresses on different planes for again 2D stress states. Okay, so here is an example problem. Okay, so here what we are given is essentially a point. You can think of this as a point P, okay, and these are the planes. So these planes are obviously very close to this point P, okay. It's very close, but I can't draw it too close, so essentially I've kind of blown it up. Essentially, you can think of this point and you have stresses on a plane that is like that and on a plane that is like that, okay. So this plane corresponds to that and this plane here corresponds to that. Okay, so essentially you know the stresses at a particular point on two different planes. Okay, and those planes essentially have their normals to be the x-axis and the y-axis. Okay, that is what is given. So that is what is represented by this diagram here. Okay, on the plane whose normal is x-axis, you have a normal stress of 30 MPa and a shear stress of 10 MPa. Okay. On the plane whose normal is the minus y-axis, you have a stress of sigma and 10 MPa. Okay, sigma is unknown. That is something that we are going to find out. And on another inclined plane here that passes through the same point, okay, we have the stresses, the normal stress to be 40 MPa and the shear stress to be tau. Okay, that is something that we have to find. Okay, so what I want to emphasize is that if you think of this as A, B, and C, okay, we have this point P, okay, on the plane that passes through point P, okay, which is AB, you have these stresses. Okay, at the exact same point, a plane that goes like that, you have these stresses. Okay, and at the exact same point, the plane like this, you have these stresses. Okay, so something that you must keep in mind, we are looking at a point and planes passing through that point, and the planes, the stresses on those planes are depicted in this triangle or wedge, whichever way you want to look at it. Okay, so this is something, it's an important concept, you should not lose track of that. Okay, so let me clear off all these annotations so that it's a little bit cleaner to look at. Okay, so now we have this problem and we are given the stresses on three different planes passing through a specific point. Okay, and in each of these planes you basically have a normal stress and the shear stress. Okay, and you have only one shear stress because we are looking at 2D problems still. Okay, now of the 6 stresses, 4 of which are given to us and 2 are unknown. So sigma and tau are basically unknown. Okay, those are the two stresses that we need to find. And we are going to use the stress transformation equations to find this sigma and tau. Okay, so first thing we need to do is define our coordinate system. Okay, so in this case, I have defined my coordinate system in this way. Okay, so x is pointing to the right, y is pointing up, and my new coordinate system, x prime, y prime, is essentially aligned along the inclined plane and perpendicular to the inclined plane. So the main thing that I want to note here is that the y prime axis is perpendicular to this inclined plane. Okay, it's the y prime axis that is perpendicular, not the x prime axis. Okay, so the angle between the x prime axis and the x axis is actually 60 degrees. Okay, so this is something that is very important, because the angle that you choose for the x prime axis is the one that we'll be using for substitution into the stress transformation equations. Okay, now that is clear, let's look at what are the quantities that are already given. Okay, based on our coordinate system, this 30 MPa is going to be your sigma x. Okay, this 10 MPa is going to be your tau xy. Because this is 10 MPa here, this shear stress here should also be equal to 10 MPa, because that shear stress is going to be actually tau yx, but we know that tau xy is equal to tau yx because of the complementary property of shear. So both tau xy and tau yx are 10 MPa. Okay. Apart from that, we know what is the normal stress on the inclined plane. Okay, so sigma y prime is 40 MPa, because the normal to the inclined plane is the y prime axis. Okay, so these are the things that we know. So what is unknown? We don't know sigma, and sigma is nothing but sigma y, because that is the normal stress on the plane whose normal is the y axis. The second thing that you must note that we don't know is tau. Okay, now here you need to be a little bit careful. Okay, because this tau I have been given, I have essentially denoted this tau in this particular problem going downwards along the inclined plane. Okay, that is my direction of tau. Now the question is whether this direction of tau corresponds to tau x prime y prime or minus tau x prime y prime. That is something that is very important, because that matters when you plug them into the equations. So now if you think about this, this is the plane. Okay, so the normal to the plane is the y prime axis, and this is the x prime axis. Okay, so if you look at this direction of shear tau here, the normal to the plane is the y prime axis, but the direction of shear is along the minus x prime axis, which means that this tau here is actually minus tau x prime y prime, because it is in the negative direction, negative x prime direction on a face whose normal is the positive y prime direction. Okay, so this is something that is very important. So tau is minus tau y prime x prime, and we know that tau y prime x prime is same as tau x prime y prime. So essentially this is going to be equal to minus tau x prime y prime as well. Okay, so this is an absolutely critical thing that you must keep in mind. Okay, so this sigma y is equal to sigma because the normal to this face is minus y, but the direction of the force is also on the minus y. So sigma is positive sigma y, not negative sigma y. Okay. On the other hand, the tau that we have here is minus tau x prime y prime, not plus tau x prime y prime. Okay. So now that we know all these quantities and we have two unknowns, and we know what the theta is, which is equal to 60 degrees, then you can actually start using the equations. Okay. So now in this case, I know sigma y prime. Okay. So I use the equation for sigma y prime. Okay. I know theta, I know sigma x, I know tau xy, but I don't know sigma y. Okay. So if I use that equation, the only unknown is this particular sigma y. Okay, that is the only unknown. Let me just erase this. Okay, so this is the unknown. Okay, and this is known. All the other quantities are known. So essentially, you can plug in the value of theta into these equations and then solve for sigma y. Okay, and if you do that, you essentially get a value of sigma y to be equal to 104.64 MPa. Okay, and that is your unknown quantity sigma. So we have found one of the unknown quantities. Now once we find sigma, we can use the equation for tau x prime y prime to solve for the other unknown, which is tau. Okay, so we know that tau is actually minus tau x prime y prime. We know what the equation for tau x prime y prime is. So we use that. Tau x prime y prime is this. Okay, that is equal to minus tau. Okay, and in this equation, everything is known. We already were given sigma x. We just solved for sigma y. Tau xy is also known. So then you can solve for tau. Okay, and tau turns out to be minus 27.32 MPa. So what does this actually mean? Okay, we assumed tau to be on the downward direction in the x prime in the inclined plane. Okay, now we get a negative value for tau, which means that the shear stress is actually going up the plane. Okay, not down the plane. Okay, so that is what this particular thing emphasizes. And what that actually means is that your tau x prime y prime is actually minus tau. So that is going to be 27.32 MPa. So that is a positive value. So if you look at this inclined plane, if the shear stress on that plane is going up, this is the y prime direction, that is the x prime direction. So on a face whose normal is the y prime axis, the shear stress is along the positive x prime axis. So tau x prime y prime is positive. Okay, so that is our two unknowns, sigma y or sigma and tau, that we have found using this stress transformation equations. So what I'm going to do next is actually solve this exact same problem. Okay, we're not going to make any changes. The only difference is that we are going to change our x prime or y prime coordinate system to a slightly different system. Okay, so it's the exact same problem. So our answers should be exactly the same. But all that we're doing is that instead of choosing this as our x prime and that as our y prime, we're going to do it slightly differently. Okay, so let's see what happens then. Okay, so everything else is the same. You can go and check back that this is exactly what we had in the previous case. The two unknowns are sigma and tau. That is the one that we're supposed to find out. But here I have made a change. So I have chosen my x prime axis to be here. Okay, and my y prime axis to be here. Okay, again they are perpendicular to each other, but then I have rotated them by a further 90 degrees about the z-axis. So now the angle between x and x prime is not 60, but rather 150. Okay, so that is a big difference. That's something that you must keep in mind. Okay, everything else is the same. Okay, so what the information that we are given is the exact same information as we had in the previous problem. Only thing is we are now analyzing it with a different coordinate system. Okay, so this is again just a recapitulation of what we knew previously. Okay, so sigma is sigma y, but one difference is that in this case though, if you look at this case, your tau, which we are assuming it to be again going downwards, the tau actually is equal to tau x prime y prime, not minus tau x prime y prime. For the simple reason, now this inclined plane, that is your x prime axis, that is your y prime axis, and your tau is going this way. So on a face whose normal is the x prime axis, the direction of the shear is along the y prime axis, which means that that shear is a positive shear. So in this case, tau is tau x prime y prime, not minus tau x prime y prime, because we have rotated the coordinate system. Okay. Now there is also some difference. In this case, because this x prime is the normal, your sigma x prime is 40 MPa, not sigma y prime is 40 MPa. Okay, but otherwise everything else is the same, and of course the theta is different. Okay, so what we know here, so we use the equation for sigma x prime now, not sigma y prime. Okay, so in this case, sigma x is known, this is unknown, sigma y is not known, tau xy is known, and sigma x prime is known. Okay, so the only thing that is unknown is sigma y, and if you plug in the values with theta equal to 150 degrees, sigma x equal to 30, and tau xy equal to 10, we essentially find out sigma y is 104.64 MPa. This is the exact same value we got in the previous problem because the direction of y has not changed. Y is still pointing in the same direction. So sigma y should still be 104.64 MPa. Okay. Now, if you now look at the tau equation, it is going to be a little bit different because last time tau was equal to minus tau x prime y prime. Now it is equal to tau x prime y prime because we have changed the coordinate system. Okay. Now we know what is the equation for tau x prime y prime, which is this. Okay. Now we know what is sigma x. We just found out sigma y. We know what tau xy is, and now we solve for tau, and you find that tau is minus 27.32 MPa. Okay. So we are coming up with the exact same value. So tau is still in the opposite direction to what you have assumed. So we assume tau is going down. We get a negative value for tau, so which means that the actual shear stress is going up, not down. Okay, so physically the same thing is happening. Okay, but now tau x prime y prime is minus 27.32 MPa, and that reflects the fact that we have rotated the coordinate system. Okay, so the physical direction of the stress is not changing because the problem is the same. On the other hand, the value that we get for tau x prime y prime is now negative of the previous value simply because we have rotated the coordinate system. Okay, so this essentially tells you that the shear stress that we calculate is essentially dependent on the coordinate system. Okay, so that's why we don't pay too much attention to whether it is positive or negative, right? So when we calculated maximum shear stress, we didn't worry about what the minimum shear stress was because it was the same value with a negative sign. That's it, right? So since the shear stress depends just on the coordinate system, we mostly focus on the magnitude of it. But for the normal stress, it's a different case. The normal stress, if it is positive, tells you whether a point is being pulled or pushed into. So if it's a positive stress, positive normal stress, then you're actually stretching something. Okay. On the other hand, if you are having a negative normal stress, then you are squeezing it. Okay. So there, the physics is quite different. Okay. But in this case, when it comes to shear, it's just a question of what coordinate system that you're using. Okay, so sign matters a lot for normal stresses. It doesn't matter so much for shear stresses. Okay, I hope this problem kind of clarifies this concept because we are looking at the exact same problem. Just by changing the coordinate system, we are getting a different value for tau x prime y prime. This is just the negative value. Okay, so this is the way we use the stress transformation equations to find out stresses on arbitrary planes like tau. Okay. Or normal stresses also we can find. Okay, that is something that we did. Okay. Now we are going to use force equilibrium. Okay, where we don't actually have to use these equations, but just using equilibrium of forces, we can find stresses in arbitrary planes. Okay, and that is what we're going to do next. Okay. So this is a fairly simple example. So in this case again, you have a wedge. Okay, you must by now know what this wedge actually means. Okay, so if this is point P, you essentially have known stresses on a plane like that, you know some stresses on a plane like that, and on a plane like this. These planes are all passing through the exact same point. So we are looking at stress at a point that on different planes that pass through that point. Okay. So in this case, we are given some stresses. Okay. So we are given that the stress on this plane is compressive. It's a minus, it's negative stress of 40 MPa. And we are given the shear stress is this. Okay. And we are also given that the normal stress on this inclined plane is that. Okay, that is 40 MPa. Okay. So on problems like this, where you asked to use force equilibrium to solve for unknown stresses, there are two important things that you need to do. Okay. First, identify whether a stress is positive or negative, whether it's compressive or not. Second is you determine what the areas are. Okay, so you're given a wedge here or a triangle, whichever way you look at it, right? You're not given particular areas of this or particular lengths of this triangle, right? But based on the geometry, you can find out what the ratios of these areas are. Okay, so what we essentially do is in all these cases, we assume that the area of the inclined plane is some arbitrary area A. It could be A or delta A, whichever way you choose. Okay. Now, if that is delta A, if this area is delta A, then this area here is going to be A cosine theta, or A cos 30 in this case, which is going to be root 3A over 2. And this area here of this plane is going to be A sine 30. Okay. So this comes from simple geometry. So something that you must be able to do and do it correctly. Because if you get the areas wrong, then the entire problem is going to be wrong. So first, you assume an area for the inclined plane and find what is the area of the perpendicular faces, okay, with respect to that particular plane. Okay, so first you find out the areas. Okay. Once you find out the areas, it's actually quite trivial to use this method to find out the unknown stresses. Okay, so what you're going to do is, we know that any point is inside the body is going to be in equilibrium. Okay, so if you look at this wedge is also in equilibrium. So sum of all forces in the x direction along the wedge for the wedge should be equal to 0. Okay, so we start with sigma fx equal to 0. Okay, so here we need to find out what are the stresses that will contribute to a force in the x direction. Okay, this shear stress is vertical, so it should not contribute. This sigma here is vertical, so that should not contribute. But all the other stresses, the 40 MPa stress on the inclined plane, the 40 MPa stress on the right plane here, this tau, and this shear stress here, everything will contribute for forces along the x direction. Okay, so first we need to make sure that you identify all the stresses that will contribute to the force along the x direction, and most importantly, make sure that you multiply those stresses with the corresponding areas. Okay, if you forget that, then your answers are going to be wrong. So something to keep in mind, there is nothing called stress equilibrium. There is force equilibrium. So essentially you have to multiply stresses by the areas to get the forces. Okay, so let's start looking at each one of these. Okay, so if you look at this stress here, that is going to cause a force in the minus x direction. Okay, so that is why this term here has a negative sign. Okay, and the area over which that stress is acting is A over 2. So that term is minus 40 times A over 2. Okay, then let's look at this shear stress here. Okay, so that shear stress is 20 MPa. Okay, but then it is in the positive x direction. So it's 20 MPa times the area, which is root 3A over 2, and that is this term. Okay, so that is corresponding to this stress here. Okay, so we have accounted for this stress and that stress. Okay, now we have to account for this stress and that stress. So if you look at this stress, 40 MPa, you have to figure out what is the component of that force along the x direction. Okay, so this comes from pure geometry, trigonometry. So this stress is 40 MPa. You multiply by the area over which is acting, which is A, so 40 times A, and you look at the component of that force along the x direction, and that turns out to be minus 40 A cosine 60. Okay, you do the same thing for the shear stress here, and that turns out to be tau A times cosine 30. Okay, so of course both these forces are in the minus x direction. That's why you have a negative sign in front of it. Okay, so that essentially takes into account all the forces that are acting in the x direction. So now, if you look at this equation here, you can think of it as equation 1, then the only unknown is tau. Everything else is known. So I can essentially solve for tau, and that turns out to be minus 26.189 MPa. Okay? So what does it tell? It tells you that the assumed direction of shear is wrong. So the shear stress is not going down the inclined plane, but rather up the inclined plane. And the value of the shear stress is 26.189 MPa. This is how we got tau using the force equilibrium along the x direction. Now, you can do the exact same for the force along the y direction. Okay, if sigma fy equal to 0. And now, when it comes to the equilibrium along the y direction, this will not contribute, okay, and this shear stress will not contribute. But the other four stresses will contribute, and all these terms here are essentially corresponding to those four stresses. So if you look at this one, I'll just look at the first term. So that is sigma, okay. That sigma is in the minus y direction. It acts for an area root 3a over 2. So that is why you have this term. Okay? And of course it is in the minus x direction. That's why you have the negative sign. So here, all that you're looking at is the sense of the stress. Okay? So the stress sigma is acting in the minus y direction. So you multiply that by the area, that is the force in the minus y direction. Okay? So that is how we get the first term here on this equation. Okay? Now you look at the stress here, the tau xy, which is also in the minus y direction, okay, and that acts over an area a over 2, and that's how you get this term, okay. And you do the same thing for the two stresses, 40 MPa and tau, which is acting on the inclined plane, okay, and you essentially get these two terms here, this term and that term, okay. The main thing is that you multiply by the area, but because these two stresses, tau and the 40 MPa stress, are not along the y direction, you have to take the components along the y direction. Okay, don't forget that. Okay, and if you do all those things, we already found out what tau is. So the only unknown in this equation is sigma. That is the only unknown. Okay, so we know every other term in this equation, and now we can solve for sigma. Okay, and that sigma is actually your sigma y. The sigma is nothing but sigma y, and that turns out to be 43.57 MPa. Okay. One thing I want you to notice here is that the value of sigma y is positive, and that is the positive sense of sigma y, because the normal to this plane is the minus y-axis, and the direction of the force is also along the minus y-axis. So it is a positive sigma y, not a negative sigma y. Okay. So with force equilibrium, you don't worry so much about the signs of the stresses to start with. You will look at the sense in which they are acting. If they're acting in the minus x direction, it becomes a negative contribution for force equilibrium along the x direction. If it is acting along the positive x direction, it contributes to a positive force for the force equilibrium along the x direction, and so on. Okay? And then once you get the numbers, right? If you get a positive number, then the assumed directions are correct. Okay? If you get a negative number, then the assumed directions are opposite to what you assume. Okay, that is all it is. Okay, so in this case, we have sigma x to be equal to minus 40 MPa. Okay, look at that. I think that's again important. So if you look at this one here, the normal to that plane is the positive x-axis, but the direction of the force or the direction of the stress is in the minus x-axis. So sigma x is negative. Okay, that is why I have mentioned it to be negative here. Okay, okay, and tau yx and tau xy, they are also negative. Okay, this is something that you can verify yourself. Okay, because with the notations that we have defined before, on a positive x-axis face, the force is in the minus y-axis. That's why that tau xy is negative. Okay, so the signs of the stresses you need to be careful about. But for just using force equilibrium to finding out unknown stresses, you just need to look at the sense in which they are acting. Okay, you don't have to worry about whether this sigma x is positive or negative, that you don't have to worry about. You just look at whether it's going to contribute to a force in the x direction or the minus x direction. Similarly for every other force or every other stress. Okay. I hope this example is clear. We'll obviously do a lot more examples like this in your homework, and that should kind of solidify this concept. Okay. So I will see you in the next class. Thank you.